previously for the atoms. So let's look at the simplest example and draw the MO diagram, molecular orbital diagram for hydrogen. In the molecular orbital diagrams, we have orbitals that belong to the atoms on the outside and the orbitals belonging to the molecule are on the inside. So here is one hydrogen, here is one hydrogen, and in the middle is diatomic hydrogen, the molecule. And we usually see these drawn with little dotted lines showing that the 1s orbitals from those two different hydrogens combined and made the sigma 1s and the sigma star 1s. Sometimes when these are being drawn, I find it's easier to leave those dotted lines out because it just gets kind of messy. So now we put in each hydrogen on the outside has one electron and its 1s orbital. When they combine, the molecular orbital in the middle, we have two electrons, 1, 2. So we put them in the lowest energy orbital and we can have two electrons in that orbital. Now let's look at the molecular orbital diagram for diatomic helium. And before you get all cranked up saying helium's a noble gas, it doesn't make a diatomic element, just bear with me. I can draw a picture of anything. So helium, each helium atom out here on the sides of the drawing has two electrons in the 1s orbital. When these two helium nuclei come together, we now have 4 electrons and we put them in. 1, 2 in the sigma 1s. Now 3, 4 in the sigma star 1s. So I fill this from top to bottom, low energy to high energy, just like I did the atomic orbitals. Now, in working, molecular orbital theory says there must be more electrons in bonding orbitals than in anti-bonding orbitals for the molecule to exist. So if I look at this, the sigma 1s is a bonding orbital. The sigma star 1s is an anti-bonding orbital. I have 2 electrons in a bonding orbital, 0 electrons in an anti-bonding orbital. Is 2 more than 0? Yes. So we would expect that this molecule would exist. Now let's look at helium. I have 2 electrons in a bonding orbital and 2 electrons in an anti-bonding orbital. Is 2 more than 2?
No.
No, 2 is equal to 2. So, since we don't have more electrons in the bonding orbital than the anti-bonding orbital, this will not exist. Now, we also have talked about bond order, single, double, triple bonds, bond order of 1, 2, and 3 in the other theories. We can calculate bond order in MO theory as well. We do this a little bit differently. Bond order is equal to the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So now let's look at hydrogen. The bond order for hydrogen is equal to 2 bonding electrons minus 0 anti-bonding electrons divided by 2 is equal to 1. So this is consistent with all the other theories for what we thought about hydrogen, that it makes a single bond, bond order of 1. Now let's look at diatomic helium. The bond order is equal to 2 bonding electrons minus 2 anti-bonding electrons divided by 2. That's equal to 0 divided by 2 is equal to 0. So there is no bond in diatomic helium. Now, things get a little fancier when we get to the second energy level. On the first energy level, we only have one orbital, the 1s orbital. On the second energy level, we have the s orbitals and 3 p orbitals. So the 2 s orbitals can combine, just like the 1s orbitals did, and they can make this sigma 2s and sigma star 2s. There are 3 2p orbitals in each atom. That gives us a total of 6. So they combine and they make the sigma 2p, that's a bonding orbital, and we get two equal energy pi 2p bonding orbitals. We also get the pi star 2p, two equal energy orbitals, and the sigma star 2p. Now, when you look at this, you'll see that the sigma star 2p is higher in energy than the pi star. And that might seem a little weird to you, like the sigma should be lower than the pi, but this is the model we're going to work with. They're actually, for those of you that read and studied this ahead of time, as you move across the second period and you get to nitrogen, you do get an inversion in these orbitals, but we're not going to worry about that. So if you haven't read that section, skip over it when you do your reading that you all told me to do after class. So skip that section about the inversion. This is the only model we will use in this class. Okay, it's the only model we're going to use for the molecular orbital theory. So now we do this just like before. Each fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons in its 2s and 2p. So that means that we have a total now of 14 electrons. So we put 14 electrons into the molecular orbital diagram. We start at the lowest energy, the sigma 2s. 1, 2, sigma star 2s, 3, 4, sigma 2p, 5, 6, pi 2p, 7, 8, 9, 10, pi star 2p, 11, 12, 13, 14. Now, when we look at this to evaluate it, we find all of the bonding electrons. They are in the sigma 2s, the sigma 2p, and the pi 2p. Anti-bonding electrons are in the sigma star 2s and the pi star 2p. So the bond order, I have 2, 4, 6, 8 bonding electrons minus 2, 4, 6 anti-bonding electrons divided by 2 is equal to 2 divided by 2 is equal to